Hello and welcome to 50 conceptual questions answer video series. Already I have discussed three questions and today I will discuss the fourth questions. And this questions is mainly based on the interface problem. And this type of interface problem is asked different kind of competitive exam. So I hope you will enjoy it. So what has been asked in this questions that a dielectric interface is formed by two homogeneous isotropic dielectric, dielectric 1 and dielectric 2 with a dielectric constant 4 by 3 and 1 respectively. And it carries no residual free charge. A linearly polarized electromagnetic wave is incident on the interface from the dielectric 1 at a point where the unit normal to the surface is this, pointing into the dielectric 1. The incident wave, which is incidence from 1 into 2, just before it reaches the interface has an electric field vector this, where E naught is a real constant. The electric field just it crosses the interface is rotated from the initial directions by an angle. So try to understand what has been asked in these questions because it's a big statement and let me draw a figure first based on the statement. So what has been said that we have a two dielectric medium, dielectric medium 1 and dielectric medium 2, and their dielectric constant is 4 by 3 and 1. And in these questions there is no equations for the interface of two medium. However, we have the unit normal. We have the mathematical expression of the unit normal to the interface. So take a look on this unit normal. It have I component, it's have k component. That's mean this unit normal will lies in the xz plane. So based on this information, I can draw a interface like this way. Let's say this is a xz plane. This is a xz plane. This is our x-axis and this is z-axis. So it's x-axis and z-axis, and then we can think about this way. Okay, that let's say this is the interface. This is the interface, and then on the interface, if we consider one point, this point where electromagnetic wave incident on this way on this point on the interface, and this is the unit normal at the interface, and let's say this is dielectric medium 1, this is the dielectric medium 2, so unit normal will be directed towards 1. So this unit vector will have z component as well as x component. So this is the unit normal to the interface, and then what is written that look at the what is talk about the what is told about this incident wave. Incident wave is incidence from medium 1 and it's have a electric field vector is this. So look at this expressions of this electric field, and mainly if you take a look on the phase part, from there we can find out what will be the directions of propagation. So here you can see that the coefficient of t and the coefficient of z both are positive. So in this case electromagnetic wave actually will propagate in negative z direction, and it's a linear polarized wave, so its electric field is oscillating in parallel to the x-axis. So based on this we can draw like this way. This wave is propagating negative z direction in this direction, and it is incident at this point on the interface, and this incident wave have electric field parallel to the positive x-axis. That's mean this is the orientations of electric field of the incident wave. Incident wave. Then what has been asked in the questions that when this light will propagate from medium 1 to medium 2, So this is interface, this is normal. So and this medium have dielectric constant 4 by 3, this medium have dielectric constant 1. So when this light will propagate in medium 2, like this way. So it has been asked what will be the orientations of this electric field. Once you can find out what will be the orientations of this electric field, then you can find out what will be the angle between this electric field and this electric field, that is electric field of incident wave and electric field of transmitted wave. So that is the question, sir. So I hope it is clear what we have to calculate in this problem. So we have an interface, and then it's the interface of two dielectric medium of dielectric constant 4 by 3 and 4 by 1. Then light is wave is incidence from medium 1 on the interface at an angle where this unit vector is given in this problem. And also from the given data we can say that the incident electromagnetic the electric field of the incident wave is parallel to the x-axis and it's propagating in negative z direction. So when it crosses this interface, after crossing the interface, we have to calculate what will be the orientations of electric field. Once we can calculate that, then we can say what will be the angle between this electric field and this electric field. Okay. To solve this type of problem, first we have to understood what are the boundary conditions, because we can solve this problem only using boundary condition. So first we have to understood what are the boundary condition. Boundary condition. So mainly we have to calculate, in this case we have to calculate electric field orientations on the other side of the interface. So we'll use boundary conditions of electric field. They have actually two set of boundary conditions, one for electric field and another for magnetic field. So in this case we'll consider only electric field. So according to first boundary condition, what has been said that the normal components of displacement vector is discontinuous by the free surface charge density on the interface. So let's try to understand this statement first. So this is the interface of, let's say, two dielectric medium of dielectric medium 1 and dielectric medium 2. And let's say this dielectric medium have permittivity epsilon 1, this medium have permittivity epsilon 2. And then this is the normal at the interface. This is the normal at the interface. And then if this is the displacement vector in medium 2, and if this is the displacement vector in medium 1, and let's say this interface, on the interface there have a free surface charge density sigma free, then according to first boundary condition can write the normal component, the normal component the normal components of displacement vector are discontinuous by the free surface charge density, by the free surface charge density. Okay. So according to this statement, we can write mathematical expression, say d2n minus d1n. That's a normal component of displacement vector in medium 1. So this will be the normal component of this displacement vector d1, and this will be the normal component of displacement vector on d2. So this will be d2n and this will be d1n. So these two component, the displacement normal component of displacement vector d2 and normal component of displacement vector d1, they are discontinuous by the free surface charge density on the interface sigma free. And if surface is there is no free charge on the surface, then we can write sigma free is equals to 0 if there is no free charge on the surface. Then we can write sigma free is equals to 0, and if the sigma free is equals to 0, then we can write d1n is equals to d2n. That is, normal component of displacement vector will be continuous only when there will be no free charge, and if there is free charge, then these two components will be discontinuous from each other by the surface charge density. And then if you want to write this in terms of electric field, what we can write simply permittivity of second medium into the normal component of electric field in the second medium is equals to permittivity of first medium and the normal component of electric field in first medium. Okay, so we'll use this condition here also, and then also we have to use the second boundary condition. So in second boundary conditions, what has been said that, let's say it is the same interface and this is the normal to the interface, and in this case this is medium 2, this is medium 1, permittivity epsilon 1, permittivity epsilon 2, and then in medium 2 the electric field is E2 and medium 1 electric field is E1. Then in this case it is according to second boundary conditions, we can write the tangent component the tangent components of electric field are continuous. Continuous. So according to this statement, if we write the mathematical expression, so what we can write, tangent component of electric field in both sides of the interface, they are always continuous, means they will be always equal. So E2 tangent and E1 tangent always same. So in this interface, this will be the tangent component of E2 and this will be the tangent component of E1. So this component and this component, they will be always equal. They will be always continuous. So this is the second boundary condition. So using these two boundary conditions, we can calculate what had been asked in these questions. So in one side electric field is given, we know the unit normal, equations of unit normal on the interface. So first what we have to calculate, what will be the electric field on the other side of the interface. So to calculate this, we will use this two boundary condition, where first boundary condition, according to first boundary condition, we can say that in this case the normal component of displacement vector will be continuous, and then second boundary conditions, we can say the tangent component of electric field will also be continuous at the interface. So using this, we can calculate what will be the electric field on the other side. So for that, what we have to first calculate, we have to calculate what will be the electric field, what will be the normal component and tangent component of this electric field in medium 1. Once we can calculate the normal component tangent component of electric field in medium 1, then using these two boundary condition we can calculate what will be the electric field on the other side of this dielectric medium of this interface. So to first calculate this, write the expression of electric field, and again one more condition we have to understood here. You see, this is the interface, and these two boundary conditions whatever I have written here, these boundary conditions actually it's independent of time and independent of position. What does mean? Does mean that if I incident a electromagnetic wave in this interface today, tomorrow, or any other day, keeping these two medium fixed and angle fixed, this boundary condition will always remain same. And then this boundary condition will remain same if I incident this electric field here, 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 or anywhere on this interface. Everywhere these two boundary conditions will remain same. Where displacement vector, normal component of displacement vector will be discontinuous if there is free charge, and if there is no free charge then it will be continuous, and the tangent component of electric field will be always continuous. So these two boundary conditions is independent of position, independent of time. So when this electromagnetic wave incident at this interface, and this look at the expressions of this electromagnetic wave, electric field of this electromagnetic wave, it has amplitude part, is phase part is time dependent and position dependent. But since these boundary conditions will be independent of time and phase position, so we'll use this boundary condition only on the amplitude part. Only on the amplitude part. Okay. So what I can write here, okay, electric field in medium 1 is E naught I cap, and then we have equations of unit normal on the interface. What is this equation? This equation is half root 3 I cap plus k cap, half root 3 I cap plus k cap. So this is the unit normal, and then once we know the electric field in medium 1, and we also know the equations of unit normal to the interface. So what we can calculate from this two equation, the normal component of electric field at the interface and the tangent component of electric field at the interface in medium 1. So we can write here the normal component of electric field in medium 1 is U1n. If we want to write its vector form, so how we can write it? I can write it in this way. I know the electric field, and then I know the unit vector along the normal to the interface. So when I multiply these two, I'll get the normal component, magnitude of the normal component of electric field, and then if I want to write the vector form, then we have to multiply this unit vector again, because the normal component will be directed in parallel to the unit normal. So here we put these two here. What we'll get once you take the dot product of this E1 with this n cap, what we'll get a root 3 by 2 into E naught vector, and then you have to multiply unit vector again. So in this case, half root 3 I cap plus k cap. So finally, what we'll get a normal component of this electric field is uh, just multiply these two things together. What you'll get a 3 by 4 E naught I cap plus again you will multiply there, so you will get root 3 by 4 E naught K cap. So this is the normal component of electric field in medium 1. So once you know the normal component, then you can also calculate the tangent component. Therefore, the tangent component of E in medium 1 is E1 tangent. What we can write E1 tangent is equals to simply, so E1 is equals to E1 tangent plus E1 normal. So we can write U1 tangent is equals to U1 vector minus the normal component of this electric field vector. Normal component of this electric field vector. So if we put this together, this is the E1 and this is the normal component of E1. When you put this together, what you will get? You will get a normal component of electric field in a tangent component of electric field in medium 1. So what will be that electric field? You can write here E naught I cap, and then you have to subtract this normal component of E1 vector, that is a 3 by 4 E naught I cap minus root 3 by 4 E naught K cap. So this will give you E naught into 1 by 4 I cap minus root 3 by 4 K cap. Okay, so this part is done. We have already so from the electric field in medium 1 and the unit vector of the interface, we have calculated the normal component of electric field in medium 1 and tangent component of electric field in medium 1. Now what we have to do to calculate electric field on the other side of the interface, we have to use these two boundary conditions. First boundary conditions is this, where it is written that the displacement vector, the normal component of displacement vector will be continuous because there is no free charge. And if we want to write this in terms of electric field, then we can write epsilon 2 and normal component of electric field in second medium is equals to epsilon 1 into normal component of electric field in medium 1. And then second boundary conditions, we can equate the tangent component of E1 and E2. So what we can write from here, we can write so according to boundary conditions, we can write E2 tangent. So according to boundary condition, according to boundary condition, what we can write E2 tangent that we have to calculate here. E2 tangent is equals to E1 tangent, and we have already calculated E1 tangent, so we'll directly put it here. So E naught 1 by 4 I cap minus root 3 by 4 K cap. E naught 1 by 4 I cap minus root 3 by 4 k cap. So this is the E2 vector, E2 tangent vector, and also to calculate E2 vector we have to calculate E2 normal. So, and we can write also according to first boundary condition epsilon 1 E1n is equals to epsilon 2 E2n. So we know what are the epsilon 1 and epsilon 2, and we also know what are the what is the E1n. So if we put it here, from there we can calculate what will be the epsilon, what will be the normal component of electric field in medium 2, that is E2n is equals to epsilon 1 divided by epsilon 2 into normal component of electric field in medium 1. So here epsilon 1 and epsilon 2 ratio, you can simply write a ratio of dielectric constant. So medium 1 has a dielectric constant 4 by 3 and medium 2 has a dielectric constant 1, so it will be simply this ratio will be 4 by 3. And then if you write the normal component in medium 1, that's normal component we have already calculated here. I've calculated here. So put this normal component this in this equation. So what we'll get? We'll get a 3 by 4 E naught I cap and then root 3 by 4 E naught K cap plus root 3 by 4 E naught K cap. So if we simplify this, what we'll get? 3, 3, 4 we cancel out, so we can take E naught outside. So E naught into I cap plus 4 will cancel out, so 1 by root 3 into K cap. So this will be the normal component of electric field in medium 2. So in other side, opposite in second medium, we have already calculated tangent component of electric field and normal component of electric field. So therefore, the net electric field in medium 2, therefore the net electric field in medium 2 is, what will be that electric field? Can write this electric field will be E2 is equals to E2 tangent plus E2 normal, and we know the both the components, so if we write them together we will get the final answer. So you will get the final expression of the electric field in other side. So what are these two components? That this is the tangent component and this is the normal component. So when you write them together, what you'll get here? When you write them together, you will get 5 divided by 4 E naught I cap plus 1 by 4 into root 3 K cap. So this will be this is the final expressions of electric field in medium 2, and we had also the electric field in medium 1, and that was E1 is equals to E naught I cap. So now what has been asked in these questions, what will be the angle between these two vectors. So initial this E1 has only I component, but when it is when it will cross the interface, and it will have two components. It will has two components, and these components are I components and K components. So these orientations of these two electric field will not be parallel to each other. So there will be some angle between these two. So now we have to calculate this electric field, this angle. So calculate this angle. What we can say that this initial electric field was parallel to the x-axis. So once we can calculate what will be the how much angle this second electric field will make the positive x-axis, and that will be the angle between these two vectors actually. So the angle between two vectors is theta is equals to so what we can write here? We can write here theta is equals to tan inverse. So this theta we are taking with respect to the positive x-axis. So what we can write, tan inverse e to z divided by e to x. That is the z component of electric field and ratio of x component of electric field. So when you write this to here, what you'll get? We'll get tan inverse z component of this E2 field is 1 by 4 root 3, and the x component you can write divided by 5 by 4, so it will be you can write this way, 4 divided by 5. So this 4 will cancel out each other, 4 will cancel out each other, and from here what you will get a theta is equals to tan inverse 1 by 5 root 3. 1 by 5 root 3. So this will be the angle between these two electric field. So let's take a look on the options. So you can see there no such type of option where options B is almost similar, but it is written tan inverse 2 divided by 5 root 3. But what we get tan inverse 1 divided by 5 root 3. So then we can either we have to convert this in sine or cosec. So if you convert these equations into this angle in terms of sine, so or we can write theta is equals to, if we want to write this in sine inverse, what we'll get, how we can do this, we can simply draw a triangle. If we consider this is theta, then tangent normal will be 1 and base will be 5 root 3, because that is the definition of tan theta. And so this side, so we know the normal, we know the base, so we can calculate this hypotenuse. So what will be this side? Length of this side will be square root of this side plus this side. So if we write this, what will get 1, and from here we'll get 5 25 into 376. So under root of 76, that's mean 2 into under root of 19. So once you know the length of this side, so if you write this angle in terms of sine inverse, so what we can write perpendicular, that is 1 divided by 2 into 19 root 3. And again, take a look on the option. I think there is option in terms of sine. So yeah, so this is the correct answer. By sine angle will be sine inverse 1 by 2 into 19. Okay. So finally we got the correct answer here. and correct options will be C. Correct answer will be C. Okay, so I hope you understood it. So what we have to do whenever this type of questions is asked, what you have to do, first you have to calculate the normal component and the tangent component of electric field, one side of the interface, and then using the boundary conditions you have to calculate tangent component, normal component of the electric field on the other side of the interface, and from there you can write the mathematical expressions of electric field in second medium, and then you can calculate what has been asked in these questions. So in these questions it was asked what is the angle between these two electric fields. So you have already calculated it, and this angle will be theta is equals to sine inverse 1 by 2 into under root of 19. So correct answer will be C. And now I have a quiz for you. And what is it? So using the same data, what has been written in these questions, you have to calculate three more parameters. And these are angle of incidence, angle of reflections, and angle of transmission. Okay. So let me give some hint how to calculate these three parameters. So to calculate this, again, you have to draw the figure. So this is the xz plane, z-axis and x-axis, and then this was the interface, and you know the equations of normal also. This is the unit normal, this interface. And then what you have to calculate, we have to calculate that electric field is electromagnetic wave incident at this point, this way. So first you have to calculate this incident angle, this angle, and then from this interface some amount of light get reflected, some amount of light will get transmitted. So according to law of reflection, you can say these two angles will be equal. So once you can calculate this angle of incidence, then you can write the angle of reflections will also be same, and then some amount of light will also get transmitted in medium 2. So this will be the angle of transmission. So you have to calculate this angle also. So to calculate this angle, what you have to do, you can use the Snell's law at this position. You know the angle of incidence. If you write this angle of transmission is theta t, then you can write n1 sine theta I is equals to n2 sine theta t. Now what is this n1 and n2? N2 and n1, they are the refractive index of these two media, and we know the dielectric constant, and there is a relations between dielectric constant and the refractive index of any medium, and that is equals to n is equals to under root of epsilon r. So if epsilon r the dielectric constant of the medium and n is the refractive index, so you can write n is equals to under root of epsilon r. So from here you can calculate the refractive index of both medium, and then using for this unit normal, you know the equations of unit normal, you know the directions of incident wave. From there you can calculate what will be this angle. So once you know the incident angle, you can write same, you can use the law of reflection, where it is written that the angle of incidence and angle of reflections will be same. So from there you can calculate what will be the reflections angle, and then using the Snell's law you can calculate what will be the transmissions angle. So I hope you will be able to calculate it. So do this calculation and write your answer on the comment box. And if you are unable to solve this problem, then just write an email. I will send you a PDF. Thank you for watching this video. I will see you in the next video.